In this clip, we're going to compare products with direct sums. So suppose we take a bunch of subspaces. Actually, here, I'll write out the indices. So U1 through UM. Suppose these are subspaces of some vector space V. All right, then we could actually do both constructions. We could look at the product of the UJs, or we could look at the sum of the UJs. And you might say, okay, so what's the difference between these two? And they're kind of close, and especially in many specific instances. But you got to understand that this first one makes sense for any UJs whatsoever. This one over here, the sum, however, only makes sense when those UJs are all subspaces of some common vector space V, like this assumption that I put back in the very beginning here. So, so let's see. Now, in the case when we do have all UJs living inside the same V, what's the difference between these two constructions? Well, it will help us to look in this case at a map that goes from the product to the sum. And the way we define it is we say that capital gamma applied to something, from our product that looks like this, right? So we have an M tuple of things, and each UJ comes from the corresponding capital UJ. Then since each of these individual components are part of the same vector space V, we can actually add them. And that makes sense, right? Okay, and so it might be useful to think of a nice basic example. So I'll just take V to be R3, and we'll use the standard physics notation just to make things a little less bulky. So I hat is 1, 0, 0, and J hat is 0, 1, 0, and K hat is 0, 0, 1. And suppose we let U be the span of I hat and J hat. Okay, so it's the XY plane. And W is going to be the span of I hat and K hat. So it's the XZ plane. Okay, so then what we have is something that, if I sketch it on the axes, looks like this. And so our U is going to be this zone down here. And our W, our W is going to be this one up here. And so if you look at this picture here, what do we have? Well, we've got U cross V is going to be isomorphic to R2 cross R2. Because we've got two components and each one of them is two-dimensional, right? There's the U component and the, oh, sorry, I called it V, I meant W. And so R2 cross R2, that's isomorphic to R4. On the other hand, if you look at the direct sum, or if you look rather at the sum of U and W, then what you end up with is all of R3. And so this sum is not a direct sum because, in fact, U and V have something in common that's non-zero. And that something is the x-axis, which you can see from the picture. So if we consider something like minus I hat plus 2J hat comma I hat minus 3k hat. So this is an element of U cross W. For this one, we have gamma of W is equal to, and then when we add those components together, the I hats cancel, and we have 2j hat minus 3k hat, right? And so what we see from that is that anything of the form I hat minus I hat, or a scalar multiple of it, is going to be in the null space of this capital gamma map. So this is a good example to keep in mind for how the product and the direct sum can actually be, or the sum can actually be different. So with that in mind, let's go ahead and take a look at proposition 377, which says that the sum of the UJs is direct if and only if gamma is injective. So this is what failed to happen in the previous example because, of course, we had a non-trivial element of the null space. So gamma is not injective in that case. So let's see then. So for the proof, I'm actually not going to prove it. I'll just give you sort of a sketch for the idea. So we know that for a direct sum, that means that U1 summed up through UM equals 0 has to only occur when all UJ are equal to 0, right? So this is an equivalent condition for the sum being direct, and that's by which proposition was that? 144. And then if you look at this condition is actually equivalent to the null space of gamma being trivial, right? So that's the idea of the proof here. And that proposition allows us to prove a theorem which could have been stated back in chapter 1, but turns out it's really difficult to prove without knowing what a product is. So a sum is direct if and only if the dimension of the sum is equal to the sum of the dimensions. Right? Oh, I guess, yeah, sorry. I guess we wouldn't be able to state that one until chapter 2C, because that's where we first talked about the dimension of a subspace. But anyways, notice that the statement has nothing to do with products, but it turns out the quickest way there through the proof is. So the idea is that the map gamma is surjective. So the rank nullity theorem gives that the dimension of the product of the mu j's is going to be equal to, oh heck, I've run out of room. Let's zip back there. Okay. The dimension of the product is going to be equal to the dimension of the sum plus the nullity of gamma, right? And so that's just because this guy here, this is the range of gamma. Okay, so then we have the following chain of equivalences. So the sum of the UJs is a direct sum if and only if gamma is injective, and so that's by the one that we just looked at. And then let's see what else we have. So this is going to be equivalent to saying that the dimension then of the product of the UJs is equal to the dimension of the sum of the UJs. And that one is follows by 3.16, which is the proposition that characterizes injectivity in terms of the dimension of the null space. So yeah, maybe I'll see if I can squeeze that in there. So that's so that's 3.16, and then this is going to be equivalent to the one we looked at in the last clip, that is 376. That the sum of the dimensions of the UJ is equal to, and then on the right side, the dimension of the sum of the UJ. So that's this, this equality between those two guys on the left-hand side, that was 376. And so that gives it to us.